Hello and welcome to session number 18 in our course Introduction to the Theory of Semiconductor Devices. Today we'll be starting on the p-n junction, probably be taking 3 or 4 sessions, maybe a little more. Who knows? We'll see how it goes. Like all of the devices, and there are essentially 5 devices, the metal semiconductor we covered, the p-n junction, and then the next one will be the bipolar transistor, and then we're going to flip over to the right side of the chart where we're going to continue with the metal semiconductor, but we're going to stick an oxide layer between the metal and the semiconductor, and then we're going to put 2 electrodes on either side of the device, and we're going to form a field effect transistor. So each of these devices has an equilibrium chapter, as a non-equilibrium chapter. By non-equilibrium, I mean that we apply voltages, and then we have a worked problem chapter. So today we're going to start on the equilibrium device. We'll have an introduction to what the structure is all about, and we'll be looking at the different dopings both on the N side and on the P side. We have an extra button we can play with here. In the metal semiconductor, the only thing that we could play with is the work function of the metal by choosing a certain metal that has certain properties, and the doping in the semiconductor here. For example, this is probably both going to be silicon effect. I think that's the main thrust of our devices will be silicon p-n junctions, but we'll be able to play with the doping both on the N side and on the P side. And then we'll be taking a look at qualitatively, not too much mathematics, fortunately this time, the charge density and the depletion region. Just like the metal semiconductor, the Schottky junction, the p-n junction also has a depletion region. And we'll find we have depletion regions in the MOS, the metal oxide semiconductor, and in the MOS field effect transistor. And before we get started, we are going to listen to, what are we going to, Andre Rieu with a wonderful, wonderful performance of Somewhere My Love. I will see you back in about 3 minutes. Okay, so this is a rough outline of some of the things that we'll be covering in session 18. We're going to introduce the device, look at the device structure tree. Specifically, in introduction, we'll say what's the same between the p-n junction and the Schottky barrier, and then we'll talk about a little bit about what's different. We'll have a little bit to say about notations. Some of the notations in p-n junction are a little bit different than what we've been accustomed to up to now. And then we get into equilibrium in p-n junctions. We'll talk about doping. When we say non-symmetric, it means that the n side is not doped like the p side. P side, for example, might be heavily doped, the n side lightly doped, or vice versa. And we'll refer to that as non-symmetric doping. And then we'll be looking at qualitatively charge density and the depletion region, and we'll get into the quantitative aspects of both of those subjects in our next lecture. And then finally we'll be talking about the electric field, but only again in a qualitative sense. Okay. So in the way of introduction, the p-n junction has many of the same characteristics as the Schottky barrier. Specifically, the Fermi level at equilibrium, when there's no external fields, there's no voltages, just sitting there, nothing's moving. Fermi level is horizontal and straight, and that includes the p and the n type. And the Fermi levels of the p and the n type line up, and they are congruent. P levels for the EC and the I and the EV always bend down, and the N, EC, EI, and EV always bend up. So the transition to equilibrium, I'm saying transition here, is when we put the two materials together. First they're separated, and we bring them together, and that transition from separation to, for want of a better word, togetherness, intimate contact, I guess, perhaps is a little bit better word, requires charge transfer, and the charge transfer implies or requires that a depletion region is formed. Electrons move just like in the N-type silicon Schottky barrier, move from, I should say, the rectifying N-type silicon Schottky barrier. Electrons move from the silicon to the p-type. Holes move from the p-type to the n-type. And the depletion region is characterized by an absence of mobile charge, and in fact it will be at the metallurgical junction, it will be precisely intrinsic. So we say it's depleted. It's not completely depleted, but it's much less mobile charge than in the quasi-neutral region of either the N or the p-type. And the depletion region further is characterized by a width W, and the magnitude of the width W is going to depend, just like on the Schottky barrier, depends on the doping density, and the built-in potential will have the same form as in the Schottky barrier, and in fact the W will have the same form as the W in the Schottky barrier. So why we even study, it looks like the same thing. Well, not quite. There are some important differences. When we place the metal with p-type silicon, we generally were going to have a larger energy barrier than the Schottky, because there's two barriers now. In the Schottky we had one. For example, if it was just N-type rectified Schottky, we had just a barrier. On the N-type, we had one depletion region. In the p-n junction, we have two depletion regions, one on the N side of the metallurgical junction, one on the P side of the metallurgical junction, and each one will have their own barriers, own VBIs or PBIs, if you will. And that means that the barriers are generally going to be higher for p-n junctions, and it means that the turn-on voltage for forward bias is going to be a little bit greater for p-n junctions. We saw, for example, in the Schottkys that we can really turn the device on with about 0.2 or 0.3 volts. In the Schottky, in the p-n junction, it's going to require quite a bit more, maybe 0.5 or 0.6 volts, depending on the doping. Okay, unlike the Schottky barrier, where we had 2 rectifyings and 2 non-rectifyings, all structures in p-n junctions have barriers and they are all rectifying. The Schottky barrier was a majority carrier. For example, if we had an N-type rectifying Schottky barrier, the carriers for current were electrons. Here, this is really the main difference between the p-n and the Schottky. In the p-n junction, we're going to be characterized by minority carriers. And I want to explain that just a little bit further as a preview. And here's, of course, are just 2 pictures. The Schottky barrier, which shows the N-silicon and the metal. The metal here is basically the contact point. If one biases this, we put an electrode here, an electrode here. The metal is really the contact point, where P will have to have a separate contact here and a separate contact here. So if you look at the Schottky N-type silicon barrier, electrons go from the silicon into the metal, in which they basically are immediately move over to the contact, and then they go round and around and around. So the only current, the drift current, is in the N-type silicon. Whereas in the p-n junction, we have a barrier, in forward bias, we overcome the barrier, we inject electrons from the N into the P. In the N, the electrons were the majority carriers. Of course, it's N-type silicon. Once those electrons get into the P-type, it's like they're in enemy territory. They are now minority carriers. So what happens, instead of being a contact point, like in the Schottky barrier, these electrons drift. I shouldn't say drift. Nasty, nasty, nasty. They are diffused. They diffuse through the P-type silicon, and the current in the P-type silicon is a diffusion current, whereas here we just have drift current. It's drift current here, but it's diffusion current here, and it's the diffusion current which characterizes the overall current in the device. Okay, so we look at the device structure tree, and this is pretty obvious. We have the Schottky up here. We replace the metal with a semiconductor, and the important thing is that the doping in the semiconductor must be different on the 2 sides. If we have N on the right, which will be the standard form, we'll have P on the left. Of course, we could reverse it. We could have NP, but then we wouldn't say p-n junction. We'd say NP junction. Well, we're going to say p-n junction, and we're going to use the standard notation where the P is on the left and the N is on the right. And eventually, I should say eventually, but a few more sessions, we're going to add a second junction to create an NPN, or a PNP, with 2 junctions, and that is called the bipolar junction transistor. Okay, just a short note on notation. We didn't have to worry about notation in the Schottky. N is N and P is P. Not a problem. However, in the p-n junction, we can have electrons in the N, little n, no problem, but we can also have electrons in the P. So how do we denote electrons in the P-type? And that's a little bit of notation. Charge type is the big letter. The subscript will be the location of where that charge is, and then either 0 or not 0, depending on whether the structure is in equilibrium. Generally, this will not be in equilibrium, so we won't have a 0. We'll just have NP, which means that there are charges of electrons in the P-type. And if this was P sub n, it would mean that we had holes in the N-type. So that's the notation that we'll be using. And here we see that explicitly. This says that there are holes in the N-type. Okay, and now we're going to look at equilibrium in p-n junctions. Okay, so let's take a look at the energy band diagram for the p-n junction. And here it sits, and we see that there are two work functions, one for N-type silicon and one for P-type silicon. The work function for P-type silicon is greater than the work function for N-type silicon, and that looks exactly like the Schottky barrier. So if you're having a feeling of deja vu all over again, well, this is the Schottky barrier. And we know that for the Schottky barrier, the band bending is going to be equal to the difference in the work functions. For Schottky barrier, this would be the work function of the metal. And if the work function of the metal is greater, as it is in this picture, than the work function for the silicon, electrons transfer from the silicon to, well, the left side, either the metal or the P-type silicon. And if it's a p-n junction, holes will transfer from the P side into the N side. And as that happens, the Fermi levels will become congruent. And we see here that we actually form the junction. Now we have non-equilibrium. However, we have a intimate contact between the P-type and the N-type. And as the transfer occurs, electrons to P-type, holes from P-type to N-type, the Fermi level in the P-type moves up. Now, I could have kept the Fermi level in the P-type constant and moved the Fermi level in the N-type down. It doesn't matter. The important thing is they come together and they meet somewheres in the middle, depending on the doping, and that we're going to see in just a little bit. So this is a picture of the in transition, so to speak. We're moving up a little bit. We're not there yet. Electrons being transferred, holes being transferred. We're forming a little bit of a depletion region. And finally, this is the equilibrium energy band diagram for the p-n junction when we have come to the end of the transition. All the electrons that we need have transferred right to left. All the holes we need have transferred left to right. The metallurgical junction is the point right in the middle. We're assuming here that this is symmetric doping. We'll say a little bit more about that later on. There is an electric field in the depletion region on the N side, and there is an electric field in the depletion region on the there's electric field depletion on the right side and electric field in the depletion region on the left. And one of the things we notice here is that the doping on the left side is equal to the doping on the right side. Now, how do we know that? Well, we don't know it specifically up here yet. We'll see that in just a little bit. But we know it from the fact that the Fermi level is above intrinsic here to the same extent that the Fermi level is below intrinsic here. See, this distance from here to here is approximately the same distance that we have from here to here. So if this, for example, is 0.3 eV, 10 to the 15th doping, the doping on the right side, on the left side, the acceptor doping, would also be about 10 to the 15th acceptors. And the other thing we note here is that the band bending, if it's about 0.3 on the right side, it's the same as the band bending on the left side. So if it's 0.3 on the left side, 0.3 on the right side, the total band bending would be about 0.6. That is a little bit on the low side. Generally, the band bending for a typical device would be in the range of 0.8 to 0.9, much greater than the Schottky barrier. So if the band bending is greater in the p-n junction than it is for Schottky barrier, it's going to take a little bit more forward voltage to turn this thing on, to get large forward currents. For example, in a PN junction, we're talking about 0.5, maybe 0.6 volts to turn on, whereas the Schottky barrier may be 0.2 or 0.3 volts. However, when we go to reverse bias, we're going to be able to make both of these depletion regions much bigger and the barrier much greater. So we'll be able to get much smaller reverse currents than we can achieve in a Schottky barrier. Okay, so we give a little example just to illustrate this. For the Schottky barrier, again, the variable barrier is equal to the difference between the work functions, and if we have a very high work function metal like either gold or nickel, I think gold is the highest, about 5 volts, we can produce 0.9 EV. That is a really, I wouldn't say pathological, that's an extreme case, because we can't use gold and silicon anyway, because gold is a contaminant which has deep traps right in the middle. So this is not realistic. It's just for illustrative purposes. Only the work function of, this should be a big 5 here, the work function of silicon is 4.1 electron volts. So, and actually I should make one more point. Although we didn't discuss the theory here, it works out in practice you can't even get the 0.9 volts. So even if you could use gold, which you can't, you still couldn't get 0.9 EV of band bending, because there's something called Fermi pinning, which is discussed, I believe, in chapter 8, I believe, the Bardeen theory, which says you can only get about 0.66. So take that for what it's worth. Anyway. Again, typical value is 0.3 to 0.5 for the Schottky barrier. Now, how do I know this is for Schottky barrier? Because of that N here. We don't have that for the PN junction. Okay, so let's do an example. And the example that we do here is, here it is. We dope both sides at 10 to the 16th per cubic centimeter. So 10 to the 16th gives us a difference between the Fermi level on the N side of 0.36 and also a difference of 0.36 EV on the left side for the P's. 10 to the 16th is 0.36, and the way that I remember that is, because I remember it's not that great, 10 to the 15th is 0.3 EV, 10 to the 16th is an order of magnitude greater, and whenever we increase the doping by an order of magnitude, the difference between the Fermi level and the intrinsic goes up by 60 millivolts. So 0.3 is for 10 to the 15th, and 0.36 would be for 10 to the 16th. So we have a total barrier now of 0.36 plus 0.36, or 0.72. And that's what we show here. So you're probably thinking the PN junction is basically the Schottky barrier with a higher barrier. And that's true. However, there's more to it than that. And this is the critical part right here. In the Schottky structure, the amount of band bending would, of course, increase if the work function was larger. But the important thing is that someplace here, okay, here it is. This is really the critical part. I probably should have put this in italics. Further, it's not only further, it's the big deal. This is the difference. This is the real difference. In the Schottky barrier, the transferred electrons, the ones that go from the metal go from the silicon into the metal, are gobbled up. They're swallowed up. They immediately go to the contact, and then, of course, the circuit goes around and around. Here, that doesn't happen. And let me just go back to page 2 here, the second page up here. So here, the electrons transfer immediately. They're swallowed up, and the circuit goes around and around very fast. Here, the electrons, for example, the holes also transfer, but let's just take a look at the electrons. They're transferred into the P, and they don't get swallowed up. They diffuse. They diffuse from the metallurgical junction to the contact. That takes a bit more time than the process here. That's why we say the Schottky barriers are good at very high frequencies, and the p-n junctions are not so good at very high frequency. Here, the primary mechanism, or the only mechanism really, is drift current. Here, the only mechanism is diffusion current, and the diffusion current occurs for electrons on the p side, and diffusion current occurs for holes on the n side. Okay, so I suggested that, and we'll go back here. So, what the result of all of this is that instead of having the drift current equation, J is equal to NeV, or Ne mu times the field, we have the minority carrier diffusion equation, which I copied here as equation 11.1, which we have derived in a previous session. Now, which terms are going to be applicable and which terms are not going to be applicable? Well, for steady state, we can cross this out. Steady state, there's not going to be a change in time, and this is the light shining, and if we don't have light, we get rid of this one. So really, we only have two important terms, and this is the main term right here. It defines the current as a function of x, and this will be our main tool, with these two, the first two terms on the right side, being the applicable terms that we'll use when we talk about currents. Okay, so you might ask, well, it diffuses. The electrons diffuse in the p region, the holes diffuse in the n region. How long does it take for all that stuff to happen? Well, this is going to be the primary factor right here, and this will be the time that it takes, in this particular case, for electrons to get wiped out, to recombine with holes in the p region. So this, the whole term right here, and we'll study its dimensions and we'll learn how to use it. This is going to be the important term. But that is the subject for chapter 12 when we talk about non-equilibrium, and we actually talk about charge flowing, electrons flowing from right to left, and holes flowing from left to right. By the way, that's why we put the p side on the left, because the direction of the holes, which is positive, left to right, is going to give us a positive current. So we're going to bias this thing with positive on the left, and we're going to ground the right, and that's kind of the standard form that we'll be using, that everyone uses. Okay, let's talk a little bit about non-symmetric doping. So in non-symmetric doping, how do we know it's non-symmetric? Well, we go over and we look at the bulk regions, or the quasi-neutral regions. And we see that on the right side, we have a very low, not very low, but a relatively low doping of donors, because the Fermi level, while it's above intrinsic is down here a little bit, it's closer to EC than EV, it is still pretty lightly doped. But go look on the left side, on the p side. On the p side, excuse me, the Fermi level is very close to the valence band. So here we have a heavily doped, not degenerate, but quite heavily doped, maybe 10 to the 18th or so on the p side, and on the n side we have maybe 10 to the 14th or 10 to the 15th. The total band bending is still the left, the n side bending, and the p side b side bending. However, the metallurgical junction is closer to the p side than it is to the n side. Notice that the depletion region width is very wide, is very large on the n side, and it's very small on the p side. And all of that is exactly what we found in the Schottky barrier diode. The higher, we only had one barrier, but if the doping is very high, that barrier is steep with a high electric field, but it has a small width. And if the doping is light, the width is greater, but the band bending is somewhat less. So now let's take a look just in a qualitative sense, not a quantitative sense. We're not going to put any numbers in here, on the charge densities on the N and on the P side. Now this one we would assume is for symmetric doping, and indeed it is, because the charge densities are equal. The areas are equal, the heights are equal, and the widths are equal. And that's the dead giveaway. If the widths are equal, we would automatically know that the dopings are the same. And here we see the depletion region. The depletion region has the charges. Oh, excuse me, coughing today. When I say charge density rho, I'm talking about fixed charges, not mobile charges. And in the N side, the donors have given up an electron and become positive. That's why this is positive here. And on the acceptor side, the acceptor atoms, the arsenic or the boron, have accepted electrons, and they become negative ions, and that is why the negative charge, the charge density is below zero on the P side. And for a non-symmetric, we have a lower charge density, a wider depletion region, and on the P side, we have a narrower depletion region, but a much sharper magnitude. So that's the difference between symmetric and non-symmetric. Okay, just a really short note on the depletion region itself. Two factors here. The electric field, of course, we know is zero at the depletion region edge. Here's the edge here. The electric field drops off to zero. Doesn't drop off in zero dimension. There's a little bit of a transition here. We'll talk about that later on. That's called the Debye region. But certainly in the quasi-neutral region, there is no internal electric field, and that's true on the P silicon side. Also, in the quasi-neutral region, there is no electric field. The other thing that we noted in the Schottky, and we've been through this a few times, the electric field is maximum at the metallurgical junction. We're going to find that is exactly the case here. The electric field will become maximum right here, and we'll just look at that. This is for the Schottky barrier. The electric field is maximum at the junction, which is x equal 0. And I could ask the question, is this N? Oh, I was going to ask the question, is it N-type? Well, I already showed it N-type. Shame on me. Okay, we know it's N-type because the electric field is negative and it has a positive slope. And that all comes from Poisson's equation. And again, this is a repeat of what we saw for the Schottky. For a light doping, the slope is less. For heavy doping, the slope is greater. But for light doping, the depletion width is greater. And for heavy doping, the depletion width is less. Now, what would you say for this as far as symmetric or non-symmetric? Well, everything looks symmetric, so we could guess that this is, well, it's symmetric. And it is indeed symmetric. Okay. For a non-symmetric, this is the symmetric case. For a non-symmetric case, generally we're going to have a higher electric field unless both of these sides are heavily doped. Now, both of these sides on the P and this end for a symmetric was heavily doped, then we would have a curve that looks like that. We would have all this thing would be brought down, and the widths would somewhat, actually they would probably decrease a little bit. For non-symmetric, we have a large slope and the heavily doped side, and we have a lesser slope on the lightly doped side. So that pretty much does it as an introduction. There's just one more figure here, which is basically a repeat of what we've seen before. For non-symmetric, I know it's non-symmetric because of the disparities in the position of the Fermi level with respect to the valence and conduction band. And we have the heavy banding on the sharp slopes on the heavily doped side, the lighter slopes on the lightly doped side, and the total band bending is equal to the band bending on the lightly doped side added to the band bending on the heavily doped side, the metallurgical junction being closer to the heavily doped side than to the lightly doped side. This is the point of maximum electric field because it's the point of maximum slope in the energy. Okay, so we've gone through pretty much everything we wanted to go through. Let's end our session with a wonderful video clip from the incredibly marvelous movie, Dr. Zhivago. Listen to again, Somewhere My Love, this time sung by Andy Williams with still clips from the movie, and we'll see you next time.
Somewhere, my love, there will be songs to sing, although the snow covers the hope of spring. Somewhere I hear blossoms in green and gold, and there are dreams, all that your heart can hold. Someday we'll meet again, my love. Someday, whenever the spring breaks through, you'll come to me out of the long ago, warm as the wind, soft as the kiss of snow. Laura, my own, think of me now and then. Godspeed, my love, till you are mine again. Warm as the wind, soft as the kiss of snow. again.